Yes. Hello, everyone. We will continue today studying properties of double integrals. First, a quick recap from yesterday. So we started talking about double Riemann integrals by reviewing the one-dimensional Riemann integrals. And before we even talk about Riemann integral, we need to recall that there are also other types of integrals, including the Lebesgue integral, which is constructed by partitioning the range of the function instead of the domain. So if you have a function, then you just look at you partition its range and then calculate the sum. So this method has certain advantages compared to Riemann integral. So there are so in general there are more functions that are integrable in the Lebesgue sense, but not integrable in Riemann sense. But it's not sort of it can also be the other way around, right? So there are functions that are integrable by Riemann, but not integrable by Lebesgue. So an example of the function which is integrable by Lebesgue but not integrable by Riemann is the following. So you take a function like this. So you say it's equal to 1. So you define it on a closed segment, x from 0 to 1, and it's equal to 1 when x is rational. So q is a set of rational numbers, and 0 when x is not rational. So all rational numbers. So it's possible to draw, right? It just as we know, rationals are infinitely dense inside all real numbers. So there will be infinitely many values of 1s interspread between infinitely many values of 0. Of course, in some sense, there are more irrational numbers than rationals, right? Because you can count rationals, so the set is innumerable, whereas the set of reals is not. Like it's sort of in set theory, it's sort of the next sort of type of continuity, right? It's what is called Aleph 1, right? So and yes, but anyhow, so this function is integrable in the Lebesgue sense, right? Because what you do, you need to, well, you actually need to introduce what it means for the measure, the Lebesgue measure to be. But anyhow, so let me just give you the punchline. Yes, we have a bunch of points here, a bunch of points there, and then according to Lebesgue integral, there will be you should consider this kind of partition. So the area here will be equal to 1. Yeah, so because you're actually looking at the range, not at the domain. And if you look at the domain, it's not even integrable. You cannot write a reasonable Riemann sum. Right? So no matter how small the mesh you will take, it still will not make any sense, right? It's not gonna it's not gonna approximate the function. Yeah. So yeah, so this function is not Riemann integrable, but it's Lebesgue integrable. Otherwise, other than that, all normal functions like that we know we use in everyday life, well, unless you work on this kind of stuff, right? They are both Riemann and Lebesgue integrable. Right? Like if the function lies in smooth, it doesn't make much difference which way you slice the graph, or horizontally or vertically. Okay, and then yeah, and then we have well, we talked about 2D integral by using the partitions, Riemann partitions, constructed Riemann sum, discussed its meaning from the point of view of volume of the 3D solid that lies underneath the surface of the graph, and so on. And then we looked at various integrations. So the condition for the function to be integrable on a closed subset of R2 is that it can be continuous everywhere except some finite number of points and bounded. So if you just require continuity on the compact set, then it's automatically integrable, right? But if you do allow some discontinuity, you need to also include boundness. Yeah, and the Fubini theorem says that the double integral is equal to an iterated integral, or rather two iterated integrals, right? So because we can integrate it like this, right? First in x, then in y, and then in y and in x, and the answers will be the same. Okay, and then we looked at some examples. Maybe we can start off today by doing another example. So if you have an area which is not a rectangle, then we need to just do iterated integral, and then the iterated integral will go from whichever parameterization you use for to describe this region here. So if your domains, if your set is squeezed between two graphs, then you would just integrate from one to another in the right order. Any questions? Okay, so let's do one more example. So let's find the volume of the tetrahedron by integration. Right? So you have it's a tetrahedron, it's an upright tetrahedron which is embedded, which is built on the coordinate axis like this. So we would go like this. So the regular tetrahedron. So this point will be 1, 1/2, 0. And yeah, this is the origin, and this point will be 0, 0, 2. And this is 0, 1, 1, 0. So this plane here, you can write the equation for it is x plus 2y plus z is equal to 2. And so we can check that all these points, they belong to that plane. And so 0, 0, 2, 1/2, 1/2, 1/2, 0, and 0, 0, 1. And then there's a vertical plane, which is x equals to y, right? So that if you draw if you draw the integration set, it will look like a triangle, right? So it will have right, and it would go from so my original drawing is not really precise because this vertex here has coordinate 1/2 along y-axis. So it's 1 here. And so this is the triangle. And here is also 1. Okay. So right, and then we need to draw this lines because we'll need them for calculation. So this line here is so just we need to substitute z equals 0 in this equation. So this line will be equal to this x plus 2y equals to 2. Right, and this line is x equals to y. Well, just the same as the plane. So we're simply restricting it towards the plane. And our goal to calculate the double integral over this triangle is called T. So, we need to calculate the volume of this tetrahedron, which we can write as an integral of the triangle of function z of x of y, right? So we need to solve this equation for z. That gives us z equals 2 minus x minus 2y, and integrate here 2 minus x minus 2y dx dy. Okay, so that is the setup, and now we need to decide in which direction, which order we will do iterated integrals, so that it will make most sense. It will be the quickest, the easiest way possible. Well, so it looks like in order to, so if you slice this domain vertically, we'll be able to write it as a single integral, right? So because if you want to try to slice it horizontally, then there's a trouble, because you have to, the area will be bounded by two different lines on the right. So instead, we'll do a vertical slicing, right? So then we can rewrite it as integral from 0 to 1 dx. So this integral will be done last, and then we do integral over y. We need to solve it for y here, right? So here, say y is equal to 1 minus x over 2, and here y is equal to plus x over 2. So therefore, integral will go from x over 2, because it's on the bottom, till minus 1 over x over 2 of the same integrand. So to integrate the functions, it will be equal to 2y minus xy minus y squared between these two guys, x over 2, 1 minus x over 2. Integral 0 to 1 dx, and then here, yes, it's 2 minus x minus, again, minus x. Right, so minus x, 1 minus x over 2 plus x squared over 2 minus 1 minus x over 2 squared plus x over 2 squared. And so with a calculation here, 2 minus 2x minus x plus x squared over 2 plus another x squared over 2. And here they will, yes, and here they'll cancel, right? So it's minus 1 plus x minus x squared over 2 plus x squared over 2. This goes away. This goes away. So it looks like I have 1 minus 2x. I have a nice formula, plus x squared. Okay. Well, at this point, there's no point. We don't need to, well, you can complete the square or you can integrate. Doesn't really matter. So let's complete the square. So we have dx times x minus 1 squared. And now if x ranges between 0 and 1, then x minus 1 ranges between minus 1 and 0. Right, so then the answer will be equal to well, so in the x minus 1, you should call it a new variable. We should call it u here. Right, so this integral from -1 to 0 u du, which is u squared halves between -1 and 0, and that's equal to I did something wrong. Oh, because it's not because it's a square. Yes, thirds. Excuse me. U cubed thirds. Yes. Yeah, u cubed thirds, and that's equal to 0 minus 1/3, which is equal to 1/3. There we go. Questions? Good. Yeah, so always sort of do not rush to do the integration. First, sort of justify the choice of the direction and the choice of the iterated integrals. Okay. So let's formulate this list properties of double integrals. So to a large extent, they replicate those of single integrals, but the sort of for completeness, let's still write them down. So the double integral over domain D. So the function is linear, right? So if you have two functions, f of x, y, which is if functions f and g of x, y. Right, so if you do clean algebra, you know exactly what this means, right? So that's equal to alpha double integral over d f x, y plus beta double integral of dg of x, y. So that's the linear property. Then there's a monotonicity, right? So that if you have if one of the functions greater or equal than other everywhere on the domain, on D, or which or a set over which we're integrating, then the inequality persists for the integrals as well. Okay, and third, which is sort of maybe so also, which might look a little bit different from, although the formula is the same as for the single integrals, its meaning might look a bit different. It's the additivity of the integral. So if you have, if domain D is the union, is the disjoint union, right? So they do not overlap. So the symbol here means that D1 and D2, they do not intersect. Otherwise, it's not going to be true. Then integral over D of f is equal to the sum of integrals of over D1 and D2. So examples may include some stuff like this, right? So you have, say this is D1, this is D2, so and the whole thing is D. So it's important that they do not have any intersection. Otherwise, in the right you'll have more integrals, right? You have something else that you don't have on the left. So you need to subtract the intersection, integral over the intersection. Okay. So that's additivity, which of course we can use. You can first, if you know that it's easier for you to integrate over, say, one region and then integrate over the other, you do that and then you add the answers together. Then area of the region D, right, can be computed by integrating one, right, integrating the identity function over the D. So that will give you the area. Yeah, so that's some explicit way to calculate that. And using this definition, we can find an inequality here. So there's another lemma in proof. So when f of x be squeezed between little m and big M for all x and y inside D, and then the integral will be bound by area of D multiplied M, and then area of D multiplied by little m. And so it's more or less, the proof is more or less straightforward. To just compare the corresponding Riemann sum, right? So when you calculate this integral in the middle, you are taking a limit of certain Riemann sums, and for every step of the process, for every step of the process, the corresponding Riemann sum is squeezed between the two, and then therefore it will survive the limit, except that you can have maybe a less or equal sign. Question has been answered. What is the letter symbol under the shape D1 and D2? Yeah, that's D. When I write not in the Zoom window, it may not be very accurate. Yeah, so just it's this thing. So sort of D is the union of two subsets. Okay, other questions? Okay. So let's move to integration in polar coordinates. So this is our next story. 15.3. Double integrals in polar coordinates. So the idea is to rewrite integral like this as integral like something dr d theta, right? So our goal is to figure out what this integrand will be after we've done the change of coordinates. So a quick reminder about polar coordinates. Oops. Is that a point in polar coordinates, right? So a point has two different equivalent descriptions, either in terms of the Cartesian coordinates or in terms of polar coordinates. And so if you have a point xy with the coordinates x and y, then we can denote the distance from the origin to that point with r, and this distance will be r cosine theta, where theta is the polar angle, right? So and then this distance is r sine theta. So the change of coordinate goes as x equals r cosine theta, y is equal to r sine theta. Well, now you can ask yourself, well, what would you do? Like essentially what needs to be done, right? So at least on the surface, it looks like this. So you want to replace f of x, y. You want to write it as f of r cosine theta, r sine theta. So and that should definitely go into the integrand. But then the question is what to do with dx dy, right? So what will that become? And to figure this out, we need to look more carefully at the representation or presentation of those small areas in polar coordinates as opposed to the Cartesian coordinates. So in polar coordinates, of course, I'm going to do a different picture with less labels. So as we know, in polar coordinates, everything goes by radii and by concentric circles, right? So we can draw a bunch of rays like this. Yeah. Maybe that's enough. Yeah, and some concentric circles. Should have them somewhere. Okay. Oops. Get back. So, so this is how we can partition a set, a subset in polar coordinates by sort of dissecting it with a regularly spaced rays with the over increasing angle, and by concentric circles with over increasing radius. Same way as in the Cartesian coordinates, those don't have to be equally spaced. We can pick a partition, right? So in other words, we would pick a partition. Well, an analog of a rectangle in polar coordinates will be what? So what is so if in polar coordinates, if you do the partition in x and y direction, what would be the analog of that in polar coordinates? What do you think? Which shape behaves as nicely as the rectangle? Triangle? circle. Well, okay, so circle is a part of it. So circle is a part of the boundary of the thread, right? But it has to have an area, right? We're integrating over something, you know. Actually, yeah, perhaps I should add that to the previous list of properties. So if you're integrating over something that has 0 area, right, then the answer is 0. So every integral. Let me not scroll back to the page. At the bottom of the page, I'm gonna write it here. So if you have of any function, so that's why it's written dA. So the answer is 0 if area of D is equal to 0. Yes, cylinder is closer. Let me first comment on that on this thing, right? So the is that point clear? So if you have, you know, if you're integrating over something 2 dimensional, like, you know, you integrate in 2-dimensional space, and then, well, if you have a set like this, right? So then you have always some non-trivial dx times dy, right? Because it's extended in both directions. However, if this is your d, but if your d is something just like a curve like that, so piano curve aside, right? Because it's infinite, it's infinitely long. So if the curve has finite length like that, right? So then a 2-dimensional integral over this thing will be 0 of any function, right? Because it's simply it has no support, right? It's well, a scientific what people say here is that this curve as a set, it has measure 0 on the 2-dimensional plane, which sort of in layman terms means that the area of the set of this curve is 0. Why it's simple? It only has 1 dimension. We talked about it in the very first lecture. Remember that, you know, if you push it to extreme, this concept is actually quite problematic. But again, piano curve aside, and similar fractal structures. So if you have a smooth curve or piecewise smooth curve, then the answer will be 0. So yeah, I'm just saying, because some of you said circle, of course the integral will be. The reason why this is true is because, well, we just talked about it, right? It's integral over 1 of d is equal to area of d. Right? We talked about this before. And well, if area is 0, then the integral is 0. And if it's integral of 1, which is 0, then it will also be 0. That integral of so we had a formula on the bottom, right? That's saying that integral of f is bounded by, if function f is bounded, right, between big M and little m, then the double integral is bounded by the area, right? So therefore, this integral will vanish by squeeze lemma, squeeze theorem. Yeah, it's gonna not so easy to read your feedback. Okay, so I thought we should say that explicitly. Oops, pressed the wrong button. When you say it explicitly because of well, it's important. So okay, so wait a little, M and big M, I spaced for a second. Oh, it will take me time to scroll back to the bottom of the page, but we had a lemma saying that if a function f is bounded between little m and big M, right? Then integral of the function f over d is bounded between big M times area of d and small m times area of d. Yeah, that was that. Now spheres, then we so they are, they are constraints, yes. It was just to illustrate that the integral should vanish if d has no area. Okay, good. And now let's get back to cylindrical coordinates. Now, so spheres, we don't get to spheres. So to do spheres, we need to, so spheres will appear in triple integrals when we integrate over some spherical shell region. So here, these will be so-called annuli, like it's an annulus. Because what I mean by analog of a rectangle, because what I want to do, I want to take a partition in theta direction and in r direction. Right, so if you have an annulus, let's do one more picture. Right, so annulus is this thing. It's part of the plane which is constrained between the radii little r and big R. So the reason why it's the polar analog of a rectangle is because here theta, or it can be also part of an annulus, right? It's to say now we also take out, we excise a wedge here, right? So say it's this guy here. So that, yeah, so the theta varies between theta 1 and theta 2. So yes, so theta is between theta 2 and theta 1, and r is between, well, let me label, otherwise it's going to be dramatic. R1 and R2. Right. So M and different circles. No, M and M was an illustration to previous lemma, so let's forget about it. It's a different. They're not connected. So yeah. What I'm saying is that this shape here, this sector of annulus, you can think of it as an analog of a rectangle in polar coordinates, simply because that's how you would define. That's how you would define this thing. Okay. Now, yeah, so therefore, in order to well, integrate, we need to introduce the partition of what? Of two intervals, theta 1 to theta 2, and R1 and R2. And then that's how we do this partition here. So let me, here, let's say this is theta 1, this is theta 2, this is R1 and R2. And this is our angular sector. Right? It's like a cake slice only with the hole in the middle. Like, they make some kind of, in the bakeries they have this tori shaped kind of cakes or things. Yeah, and then as before, it boils down to the the right Riemann sum. We'll look at those small regions here, right? And now let's calculate what's the area of the small region is. Okay, so we can do this. We can do that quite easily, right? So in order to calculate the area, we can take the area of the sector. So we can take this sector here, compute its area, and then subtract some more fancy colors here, and then subtract subtract the area of that sector. All right, so then the yeah. Well, I hope this picture is not too good. We might get another picture. So we have two circles and then two angles. One of them will be an angle theta. The other one will be theta plus delta theta. Then we have two radii, r and r plus delta r. So we have this area here, which is squeezed between two neighboring radii, which is different by delta r, and two angles which are different by delta theta. So our task is to find the area. So as I said here, we take the area of this sector and then subtract from it the area of this sector. So what is the area of this bigger cyan, whatever this color is, sector? If you know that the radius is r plus delta r, and the angle wedge is equal to delta theta, what is the area? So if you have a pizza slice of angle delta theta and the radius of pizza is r, what's the area of that sector? One? Why one? It should depend on theta, right? So yes, r squared theta. Is it r squared theta or with 1/2? Yeah, with 1/2, right? So yeah, so that's better. So it's 1/2 r plus delta r squared delta theta. You can check this formula that if delta theta is if you have the whole circle, right? So then the circle will be equal to delta theta will be equal to 2 pi, and the area should be equal to radius squared times pi. Okay. So here angle is measured in radians, right? So it varies between 0 and 2 pi maximally, but so yeah, so that's the area. Okay, maybe I should use the same color. This way it will be even more. Yeah, so it's 1/2 r plus delta r squared delta theta. Okay, and then the area of the black sector, it's like, you have a large pizza and a medium pizza, right? And then you're calculating the difference, like how much you're overpaying between large pizza and medium pizza, right? So of course you know that it goes as a logarithm, right? So you can add on the extra buck or two, and you get large pizza from medium one. So we are calculating that market effect here. As long as my tablet unfreezes, yeah, so minus 1/2 times r squared delta theta. Okay. Okay, so let's open the parentheses. Okay, I'm going to switch to neutral color. So it will be equal to, we can take out 1/2 theta up front of the, yeah, sure, absolutely. So buy 2 pizzas, right? And then put one on top of another, and then you can calculate how much area. Yeah, so and then, yeah, so you can count, yeah, so is it is the price going up proportionally or not? So I'm going to tell you that it's probably not. Times theta, and then here we have r squared plus 2r delta r plus delta r squared minus r squared. So this leading term disappears, and then we have here two cancels. We have r times delta r times delta theta times delta r, and then there's another contribution with delta r squared plus 1/2 delta theta delta r squared. Okay, so far so good. Now, yeah, so if this difference is, so of course we'll be interested in taking, actually I should call it delta A, right? So delta A. So far it's a finite difference. We used finite formula. So far we didn't assume any notion of smallness, right? So it's you can actually make this calculation for a slice of pizza. But now let's make our pizza infinitesimally small. So we send delta theta and delta r to 0. So in other words, the mesh of those partitions will go to 0. And then in this example over here, in this expression, this thing is much smaller than that, right? Because when delta r is small, delta r squared is much smaller than delta r. So it's the next order of in expansion in delta r. So in the limit, we can neglect this thing, right? We can remove it. So as delta theta and delta r goes to 0, then delta A approaches dA, this differential of the area, which is equal to, I'm just writing, oops, equal to r dr d theta. Okay. And this is what our calculation was about, because if you come back to the thing, so that's our dA, right? So dA is dx dy. So the question was, by what we need to replace the differential, and now we know the answer. We need to replace it by r dr d theta. So this is the second ingredient that will go into the integrand, and we can now unpack. We can now sort of demystify that. We can write it as double integral f times, well, f of need more space. So first write r here, then it's f of r cosine theta, r sine theta times r double integral. Yeah. So that's how the integration in polar, that's how the change of variables in polar, in integral, in double integral in the polar coordinates works, right? So change of variables from one way to another. So in integrand, you simply replace x with r cosine theta and y is equal to r sine theta. And what is known, I think I mentioned it to you, sometimes it's called measure of integration. And then the measure is written as r d theta d, r dr d theta. Yeah, so that's what all this was about. So because of the cylindrical symmetry, because of the radial symmetry, okay, I'm going to have to rewrite that, I think. Just so the way this f works, it sometimes remembers the steps, and okay, we'll erase everything, and now I can write. There we go. Whoa. Okay. I'll correct that in the. Let's try to get out and in. I'll correct it in the PDF. Yeah. Okay. So let's look at an example of how this calculation works. Yeah. So let's say the region is given by the two circles. So there are two circles of radii 1 and 2, right? So and we want to integrate that. So that's the let's call it annulus A, right? Is given by set of points x and y on a plane such that so such that the x squared plus y squared is between 2 and 1. And let's integrate over this annulus function given by 3x plus 4y squared dx dy. So we can see that the meaning of the polar coordinates, right? It's it will be useful. It's useful to do the polar coordinates if the domain, right? If the not the function, but rather the region over which we're integrating has this circular symmetry, which of course the case here. So switching to polar coordinates, we get this integral, well, still annulus A, and then we just replace it. We have right 3 times r cosine theta. And then we can even do the limits right away. So theta varies between 0 and 2 pi. Question. Oh, I see. So that's the sort of. But the people who sell pizza, they're not stupid, right? So because they know how to attract more customers, right? So I think they're probably making money on the small pizzas, right? Like if you buy a pizza for yourself, like the personal size, then you're overpaying a little, as opposed to you buy like the family size pizza. And so the limits of theta goes between 0 and 2 pi, and r goes between 1 and 2. Plus 4 r squared sine squared theta. And first we wrote, and then r, right? So this important part in this measure, r times d theta dr. Okay. And then the well, what shall we do first? Let's do r integral first, right? So then integral from theta will stay, and then you have integral from 1 to 2 r, also dr, and then we need to multiply things together. So you have 3r squared cosine theta plus 4r cubed sine theta. So the integral here, integral 0 to 2 pi. Yeah, and then here you can just do it, right? So it's the r cubed cosine theta plus r to the fourth. I think I forgot the square inside. Yeah, that's right. Sine squared theta, thank you. Between 1 and 2. So it will be what? 8 minus 1, right? So it's 7 cosine theta plus 15 sine squared theta. Yeah, and then we integrate theta. So integral of the cosine is sine. It's equal to sine 7 sine theta. And actually, yeah, so we don't even have to integrate, we don't have to calculate it here. So we know that, let's save ourselves some time. The integral of any periodic function over the period is 0. So therefore, the first integral will disappear because it's a periodic function. And here from sine squared, we need to single out, well, the non-vanishing part, right? So let's use this formula for the doubling angle. What's the formula that represents sine squared theta via something of double of 2 theta? What shall we replace it with? Yeah, so it's 1 minus cosine 2 theta over 2. And then cosine will be unimportant for us, right? So the answer will be equal to 15 halves times 2 pi. I think there's a typo in the book, yeah. I think this answer is correct, so it's 15 pi. Because the integrator of a half circle, yeah, and never mind. Yeah. The answer is correct, yeah. So it's 15 pi. In similar example in the book, the integrator of a half circle. That's fine. Okay. Questions? Okay, let's take a 5-minute break and then like a several minutes break, and then we'll come back. Okay. Good. So now let's make the same generalization as we did before. So instead of looking at when we talked about integration in Cartesian coordinates, first we talked about rectangles and then about some arbitrary shaped areas. And now we can do the same in polar coordinates. Right, so you can imagine that there's some blob like that, which is bound between, which is a subset of some annular region. So you have some annulus that contains set D, and you want to learn how to integrate over that thing in polar coordinates. Well, so we do it in the same way, so that we simply need to, well, the idea would be to, again, to break it in two parts. So, and then you can call this branch of the boundary, we call it H2 of theta, and this part of the boundary we can call H1 of theta. And what we'll do, we will simply integrate like this between, right, so from one from one part of the boundary to another, and we'll be slicing radially, right? We'll slice along radial direction, and angle theta will vary between whatever it needs to be here and here. And then as we do so, we will slice it like that. So this brings us to, say, to the following formula. So let D be a set of points, which in polar coordinates are given by this inequality. So theta is bound between alpha and beta, and R is between H1 of theta and H2 of theta. So H1 and H2 are some functions, right, in polar coordinates. So it's R equals H1 of theta and R equals H2 of theta. So then integral over the function f over this region, right, is equal to integral from alpha to beta d theta, integral over from H1 of theta to H2 of theta, f of r cosine theta, r sine theta, r dr. Yeah, that's the formula. Right, so in particular, if you want to find an area of that region, you would just take f is equal to 1, right, and then you would integrate this thing. So you're going to have integral from alpha to beta d theta times integral over from H1 of theta to H2 of theta, just 1, right? So 1 RDR. And that will give you, well, you still need to integrate integral from alpha to beta 1/2 H2 squared of theta minus h1 squared theta d theta. And so that since the function is trivial, we can do the integral over the r, and that will give us the area. Right. So yeah, let's do an example with this. So take a function which we looked at in polar coordinates, r of theta is equal to cosine 2 theta, and I remind you it looks like this. So it's like it's a four-leafed clover, whatever. It looks like a flower with 4 leaves, and then it takes pi over 2 worth of angle theta to complete one of those blades. So let's calculate the area of one of those blades. So area will be equal to integral from, I'm just looking at the formula from above, integral from say 0 to pi over 2. And then here this function r of theta should play the role of h2, and h1 is just 0, right? So there's nothing that bounds it from below. So it's 1/2 of cosine squared 2 theta d theta. And how do we do this integral? Well, we do the doubling trick again, right? So it will give us 1/4 integral from 0 to pi over 2, 1 plus cosine of 4 theta d theta, or so so the period of cosine 4 theta is exactly pi over 2, right? So integration over this thing is equal to 0, like this integral will disappear, and the answer will be equal to pi over 8. So the pi over 8 for one blade, and then times 4 and pi over 2 for everything. Questions? Okay. Sorry. Now let's get back to our pizza slices, and then we can ask ourselves, what if pizza becomes infinitely large, right? So in other words, that's a fun problem. So far we were talking about proper integrals, but now let's include improper integrals, when the region of the integration, when the size of the domain of integration becomes sort of becomes infinite. Improper integrals in polar coordinates. And we'll solve two problems at once. So first, you probably seen this integral before. Does anybody remember what is it equal to? Yeah, that's the bell curve. Yeah, so we will now study its two-dimensional analog. So think of a bell curve. Now we'll think, yeah, let's get back to pizza. So say, that's right, it's equal to square root pi. So let's find this formula. Let's find the answer. So this function e to the minus x squared is famous for not having an antiderivative. But we can still do improper integrals with it using analytical methods. So I'll give you the derivation for this result using a using the I don't remember, is it 2 root pi? Yeah, I think it's correct. Using integration, double integration polar coordinates, and the reason why I say it's back to pizza is the following. So let's call this integral I. Okay. Now and now let's take I and multiply it by itself, right? So consider I squared. So let's write it down, right? So it will be integral from minus infinity to plus infinity e to the minus x squared dx, and then we'll multiply it by itself. Well, now we have to introduce a different variable, right? Because no, it's different. X and y here are independent. Now, remember what I told you about iterated integrals, right? So if the function is factorizable, we can replace it. So yesterday we went in different directions. So we have a double integral of a function of two variables, and if the integrand factorizes into product of the functions, then we can factorize the integrals. Now let's read that statement backwards. We will write it as a double integral. So it will be double integral from minus infinity to plus infinity, from minus infinity to plus infinity of e to the minus x squared minus y squared dx dy. Right? So remember that should be equal to I squared. So if you find this integral, we'll find square of I, and then therefore we'll find I. Okay, and now that's we looked at this function previous week, right? If you draw it, if you make a 3D plot of this function, it would look like a hill, like a mountain, which would exponentially decaying slopes. So in terms of pizza, you can think that you're making a pizza and putting some cheese or salami or whatever, and then you throw in more in the middle and less towards the edges. And let's assume your pizza is infinite, and you can ask yourself, will we have enough food, enough stuff, enough salami, enough toppings to put it on, right? Because integral converges, that you can do this with finite number of stuff. Now, how shall we calculate this integral? Well, we'll use polar coordinates. So we'll replace this, as you know, is replaced by r dr d theta, and that is replaced by minus r squared. So in polar coordinates, it looks like integral from 0 to 2 pi d theta, and then integral from 0 to infinity, right? Because it's we're integrating over the whole plane, dr e to the minus r squared times r. Right? So integral before e to the minus x squared does not have an antiderivative, but integral of x e to the minus x squared does, right? Because we can make a change of coordinates here. We can say that we can put r inside, right? So this integral is equal integral from 0 to 2 pi d theta 0 to infinity e to the minus u squared du, and there is a factor. There's 1/2 factor here. So if u is r squared, then du is equal to 2r dr. And now we can do the integral, right? So now it's equal to 1/2 integral from 0 to 2 pi d theta e to the minus u without squared. That was the whole point, right? Yes, so e to the minus u between 0 and infinity. So this integral is equal to 1. So that thing is equal to 1. And then the integral is equal to pi. Right, so I squared is equal to pi, therefore I is equal to square root of pi. Well, we know that it's positive, right? So therefore it's equal to square root of pi. So yeah, you have pi units of salami or cheese or Italian sausage to put on your infinite pizza, which is. Oh, 1/2 got cancelled because so integral over theta goes from 0 to 2 pi. So you have 2 pi multiplied by 1/2. Yeah. That's okay. Yes. So here's another example of improper so application of integrals in polar coordinates. Okay. Yeah, so if you do want to do this research project about pizza prices, you can plot all the prices of pizzas starting from single person to extra large one and see if you can extrapolate it to infinity, right? So what will be the price of infinitely big pizza? Is it going to be infinite or finite? Yeah, sure. Okay. Okay, so our next story are some applications of double integrals. 1.4. Some physics applications, which bring a lot of examples to calculate. So one of them will be, the first one is mass and density. And so if you have a solid, let's say, brick of metal or whatever, and then you know its volume, right? And you know its density, right? So you know that the mass is equal to density times the volume, right? Or you can use this as a definition of density. So if you know that this material is uniform, which means that if you pick a small portion here or a small portion there of equal volume, they would have the same mass, then this will be the formula. But of course, you understand that in nature, almost nothing is uniform. And then the density is a function of coordinates, right? It changes. So for example, the air in the atmosphere, right? So this density of the air is bigger where we live than above in the mountains, right? So when you go, what's it, to 10,000 feet, it's what, like 30% of the air, of the pressure and so on. You know that if you go above the 11 or 12,000 feet, stars do not twinkle anymore, right? Because the air is too thin. Yeah. So there's some distribution of density of air as you rise up in the atmosphere, and it appears everywhere, right? So some media like water are almost incompressible, so the density of water, even if you go deep in the ocean, almost doesn't change. There's slight variations, but they're really small. But yeah, in general, we should think of mass. We should replace this formula by an integral, right? So and here, so here we're talking about 2 dimensions, right? So I draw the 3-dimensional thing. So say you have some, 2-dimensional shape, right, in X and Y plane, And then density is a function, right, of x and y. So the mass will be integral of the density function over the volume. Well, area in this case, right? The same applies to the 3 dimensions, so we do the 3D integrals, but for this particular application, you can think of it as not having the 3rd dimension, right? It's just some sheet of paper or sheet of metal or anything. Yeah, so that will be the formula for the mass. There's a similar formula for electric charge, right? So say you have a charge, and then again, it's a well, area. Let's put area here. It's some area integral over the charge density. Well, I'm going to put C here, which designates electric charge, dx dy, and you would compute the total charge of this planar of this 2-dimensional object. Yeah. So yeah, I put C, which sort of stands for charge. The function is rho, right? That's the density. That's what typically done in physics books, right? So let's do an example. So you have a metal plate of triangular shape. So it's 1, 1, and then say the density, the charge density behaves as x times y, right? So the density is higher when the product of x and y is bigger. Right, so let's find the total charge of this plate. So total charge will be integral over this, let's call it d, x times y dx dy. And then, for example, if we can deal with the vertical slicing here, we would kind of integrate first over y coordinate and then over x, but it doesn't really matter. So this equation here is y is equal to 1 minus x. And then therefore the integral is equal to integral from 0 to 1 dx, integral from 1 minus x to 1 xy dy, which brings us to x y squared over 2 between 1 minus x and 1, or it's integral of 0 to 1 x half minus x times 1 minus x dx. Right, or it's integral from 0 to 1 so this is x half minus x, or squared. I think I forgot the square, guys. I'm sorry. This is square. There's a square here. Yeah, because it's y squared. And there's a 1/2 also. So we can take out 1/2 here. And here we have so without the half, it will be equal to x minus x plus 2x squared minus x cubed. That disappears. It's equal to that time 1/2 times so it's 1/2 2/3 x cubed minus x to the 4th over 4 between 0 and 1, and that's a half times 2/3 minus 1/4. So that's a 5 over 24. That's the total charge. Next physics application, mechanics application, is moments and center of mass. Yeah. So what is this? What is this center of mass? Again, let's think of some two-dimensional shape, which sort of lives in a plane, and then a center of mass is a point. So you can kind of tip it. You can rest the whole body on a needle, which is pointed towards the center of mass. Now, of course, can you actually do it? Probably not, right? Because there will be some instabilities, like as the body will start tilt a little due to some oscillations, it will eventually fall off, right? So it's not a stable position, but of course you'll know how to balance, a spoon or a pencil on your finger. And the reason why I can do it on your finger is because finger is not actually point-like, and then the friction between the finger and the pen or the stylus prevents this thing from falling. So let's learn how to how to find the coordinates of center of mass using our methods. So what we need to know, right, is the density of this material as a function of x and y, right, and its dimension, right. So which equations describe its shape, and the formula for the x coordinate of the center of mass is this. It's 1 over the mass of the object multiplied by the, let's call this region D, multiplied by the integral over d of x times rho of xy dx dy, and y coordinate of center of mass is equal to 1 over the mass of the body, integral over d rho of xy times rho of xy dx dy. So if you remember the formula for the density from above, right? So then, in a sense, mass, you can think of mass as the average of the density over the region. So you can write it like this. You can write it as a ratio of two integrals, integral over dx times rho, let me write it short, dA divided by double integral over d y, excuse me, rho, just nothing, just rho dA. Right, so in other words, what you're doing, you're averaging, right? We're averaging x over the density function of the shape. And there's a similar formula for y, right? So that's for the y positional center of mass, it's the integral of y times rho dA divided by the mass. And then sometimes this is called the numerator here. Numerator here is called the y moment, and sort of it's complementary. And the numerator in y is called the x moment. So it's moment about y-axis. It's because it's basically it's yeah. And then this is this moment about x-axis. Yeah. So it goes it goes complementary. So probably in physics class you will find in center of masses of point particles, right? So for example, where will be the point mass of sort of application? Yeah, we'll get to this later. Let's first do the regular example, and then I'll talk about point masses. Take a triangle here. So there's a triangle with coordinates. So this is point 0, 2. One, 0, 0, 0. And let's say it's the density function here is a linear function. Let's find the coordinates of the center of mass. Right, so by our formula, x the coordinates of center of mass. So if we do somewhere here, so in order to find the coordinates in the x direction, you would integrate. Yes, you would this integral over x times 1 plus 3x plus y dx dy. We'll just need to calculate a bunch of integrals, right? So we need to calculate the let's calculate them separately, right? So the moments and the mass. So yeah, so this is called the mass. Let's calculate it first, because it will be used to both integrals. So this line here is given, the equation for this line is y is equal to 2 minus 2x. and say we're doing the vertical slicing, so it's integral over x from 0 to 1, and then integral from over y from 0 to 2 minus 2x. And because that's where the it changes. Yeah, and then just integrate the function 1 plus 2x plus y dy. Which in turn equals to y plus 3x, y plus y squared halves between 0 and 2 minus 2x. So it's 2 minus 2x plus 3x 6x minus 6x squared plus 4 minus 8x plus 4x squared so that's minus 2x minus 2x squared there's no not minus 6, minus 4x minus 4x minus 2x squared plus 6, right? Okay, did I make it? Yes, I think it's right, minus 2x. Should be 8. Made a mistake somewhere. I divide by 2. Oh, that's right. Yeah, so sorry. Forgot to divide by 2. Okay, let's get back. Getting tired, right? So we need to divide by 2 here. So therefore, yes, so it's equal to yeah, so if you divide by 2, we'll get 2 minus 4x plus 2x squared. And here we have 2 minus 4x plus 6x minus 6x plus 4x. Excuse me, minus 6x squared. Why is it minus? Sorry, so I'm getting slow on this. Yeah, so 2 plus 4x minus 6x squared. And then if you add it together, right, so you're going to get 4. Yeah, so this cancels. Yeah, now I think it's good. Yeah, 4 minus 4x squared. Yeah, good. Now it's fine. Yeah, so that's equal to 4 integral from 0 to 1 minus x squared dx. which is given to 4x minus x cubed over 3 between 0 and 1. And that equals to 4, 1 minus 1/3, which is 8/3. There we go. Question: are you writing y center of mass for the general point? No, it's the not the general point. It's the coordinate of the center of mass, right? So that's the formula that we're using. So it's at this point here. So if you put a needle on this point, and the triangle should stay. It's where all this mass is as if all the mass is concentrated there. Like if you throw a triangle, it would fly. If there's no resistance, it will fly over parabola, right? And then a center of mass will fly over the parabola. CM stands for center of mass. Yes. Yeah, so it's both for x and for y. Yes, it's. If you go above, I think I had it both here. Yeah, see on the left, on the top left. These are coordinates. These are the coordinates of the center of mass. Couldn't tell. Oh yeah, sort of. Well, I mean, yeah, okay, sure. Okay, now so we found the mass. Now let's find the moments. Let's at least found one. Kind of running out of time, but let's find. So this is called. This moment is my. Let's find my. Essentially, it's the same integral. Only the well, we'll do the same, right? So we integrate from 0 to 1 dx, and then what we'll have here will be integral of that, right? So to speed it up a bit, so it will be integral from 0 to 2 minus 2x of x plus 3x squared plus xy, right? Dx dy, excuse me, and then you would have an integral from 0 to 1 dx, which looks like well, again, there's some calculation that you need to do, which I think you can do it as an exercise. And after integration, it will be equal to x minus x cubed, which then brings us, so this integral will be equal to 1. So the position of the x center of mass is equal to 8 divided by 8/3, which is equal to 3/8. So here at this point is 3/8. And similarly, you can find the coordinate, the y center of mass, coordinates of the y coordinate of the center of mass. It will be equal to the mx divided by the mass. And after the calculation is done, so there will be more exercises at home, then it will be equal to 11 over 16. Point is 11 over 16. Okay. Try it at home. If you want to succeed, let me know. It's also in the book. And besides that, there will be more. There will be a lot of exercises in homework. Right. So we'll also talk next time. We'll talk about, finish with that. Talk about momento of inertia. And yeah, expected values, and then we'll go to triple integrals. Oh, then there's also surface area, and then triple integrals. So it's a big chapter. Yes, and then probably part of the discussion on Friday will be about. I'll lecture a little bit more, and then we'll talk about some problems. So I encourage you to look at the homework, as soon as possible. So if you have any questions, ask me, whenever you're ready. So on Wednesday we'll have a quiz about the previous week. The Lagrange multipliers, minimum and maximum. On Wednesday. Oh, sorry, Thursday. Yeah, quizzes on Thursday. Yeah, tomorrow we'll continue lecturing. Excuse me. Great. Yeah. Any other questions? Yes, correct. Yeah. Okay, thank you guys. I'll see you tomorrow. Bye.